Olaf Schmidt from INCHRON. I'm responsible for business development, and I would like to take you to this presentation, the first half and the third half, and in the middle we have Armin from iSYSTEM. So this presentation is about worst case timing measurements, especially for ISO26262 safety critical control units. And my agenda for today is I will show it in a minute. So this is based on a paper that was published at the ESE Congress in last December. A presentation we have done together with iSYSTEM, but also with Open Synergy and Volkswagen. The idea of Volkswagen was a study by Volkswagen was about how can we integrate virtualization into our into their control units. So the people involved into this project and presentation were from Volkswagen, but as well as Armin, Ralph, who's our CEO, and Philip, who's also online today, and myself. So the agenda for today is about how would we approach these safety critical applications, and we propose to start on the architecture and design phase. So you would start with system level requirements, you would derive technical and requirements and event chains from the system level requirements, and also create a system architecture at the same time. We would also look at simulation worst case analysis, and then derive again a software architecture and look at simulation again. And then after working on the more theoretical parts, after software is implemented, you would actually analyze the system that is actually running with iSYSTEM tools, and Armin will later show how this is done. And from the results of an implementation, we would actually derive a virtual target so that you can run additional tests on the dynamic behavior on the results that you get from the target. So as you see, our focus at first is on the two parts here on the lower left, and then the real testing in the middle. So this is how a system, and especially the timing related things look like. And this was the system that was examined in the project, and could be similar to the systems that you actually have. This is a system that includes a hypervisor that has, of course, its own scheduling inside the hypervisor, and then we have a number of virtual machines on here with their own scheduling. So it's looking forward a little bit, because hypervisors are not so established yet, but the same mechanisms will of course work if you don't have a hypervisor. So looking at a system with hypervisors, the hypervisor provides a way to split the overall system in virtual machines, which means that these virtual machines will run independent of each other, and they will basically take a bit of time each time they run. And the hypervisor uses a TDMA type of mechanism, and it will more or less execute one VM after the other, and then will switch between the VMs. So if you have a hypervisor timing cycle like this, then this time will be split into smaller chunks for each virtual machine. And this is also called time slice for each virtual machine. And then, of course, you have your application and your tasks, and one step is mapping these tasks to the different virtual machines. And as you can see, there are some tasks that are only running in one virtual machine, but this T10 millisecond task, the designer decided to run it also in other machines. So this is a critical concept of looking at timing. So you have available timing, you have your tasks, and you need to distribute your available processing time to the different tasks and assign that. From a setup, we have been using a setup that is being derived a bit from an ADAS system. So here you would have a camera, you would have a central controller for data fusion, and maybe a radar sensor. So all of these may be used in an ADAS system. And on each of these systems, and that's what we used in this example, we run a hypervisor on a Renesas RH850 board, and in order to see what's actually going on the board, the iSYSTEM blue boxes were attached to each of these boards, and the actual timing behavior could be recorded and traced by these boards and then displayed in the INCHRON tool suite. So, but as we usually start at modeling and on the simulation side, you can see here that we have created a model with these 3 units, and in each of these units you will see the hypervisor and different virtual machines that have their own scheduler, and then we have some tasks inside the virtual machines. One very interesting part of systems like these is the data that is actually flowing through these different tasks, these different virtual machines. We call them event chains. So in the model, we would also model the event chain, which is basically data flowing from one task to the next task to the next task, flowing through this overall system. So in the end, it's not also important that the data is flowing through, but it's very important that the timing of the data is correct. So all the data has to arrive at a certain point in time, for example, here in the data fusion, and it may have different paths of data coming together at a certain time, and the repetition and jitter has to be monitored and has to work in a certain way. So looking at the timing diagram, so for example, in this timing diagram, you can see the timing of the hypervisor. You see this blocks here, which represent the TDMA slots of the hypervisor. Then I put in some virtual machines and some tasks. So you can see that the different tasks here running on the different virtual machine. For example, the VM2, these 3 VM2 tasks run here in the time slot where the VM2 is active, and the VM3 task runs only in the TDMA slot where the where VM3 is active. So this can be derived easily from the model, and we can just execute the model in a form of a simulation. And then you will see that here is a very short response time. So this task is activated, and then after a very short time, you can see that it's actually calculated and ready to go. There's also other tasks that are activated down here, and as they have only time during the VM slot, it may even take multiple slots until they are completed. So the design of the slots and the length of the tasks and the assignment of tasks to slot is a very critical design criteria that you need to have a look at when you design such a system. Yeah. And of course, we can put define requirements that we have on this task, like a certain response time, and we can monitor at all times if these requirements are successfully met or not. So that's kind of what we can do on the left side here. So after creating the requirements, we use a simulation and a worst case analysis to see if our requirements are met, and we can do this in cycles step by step and optimize our system architecture and our software architecture. So timing and performance would at the end be checked based on models and simulation before we go to the implementation. But of course, the next step is then to implement the system, and with the implementation, which of course is not part of this talk today, but with the implementation, you would like to have a look at what's going on in the implementation. And so the next step is to measure what comes out of the implementation. And here I would like to switch over to my colleague Armin from iSYSTEM, and I'll be back for the last part then. So please give me a minute to switch. So. Okay, Armin.
Okay, also welcome on behalf of iSYSTEM to this webinar. My name is Armin Stingel. I work as a systems engineer at iSYSTEM since about 5 years. Yeah, my task is now to try to explain to you how such a complex system can be actually traced on the real hardware. On the first picture, I first want to give you an overview about the overall trace setup that we're using here. Just for simplicity here, I'm just showing 2 of the ECUs, but actually the concept that is used here is absolutely scalable, so you can extend it to virtually any number of ECUs. As you see, the exact same trace setup is used on each of the ECUs. You can see here an IC5700 blue box is used to record the program and the data trace of the RJ50 ECU through this parallel Nexus port. This means that we're tracing on instructions and the data accesses performed by the CPU, by the software running on the ECU. And in addition, we have this CAN-LIN box down here, which is attached to the IC5700. This blue box actually traces all the communication going on this shared CAN bus. And the unique thing about this setup now is that the trace timestamps between this CAN bus recorder and the software trace recorder are now synchronized in a special method that we have implemented. This means that this setup allows to trace the software activities and the CAN bus communication synchronously to each other. And since the same trace setup is used on both ECUs and both ECUs share the same CAN bus, this CAN bus can basically act as a common time base for this setup. And as you will see later on, such a common time base is required for the correlation of the multiple software traces that we have recorded from the various ECUs. And this is obviously needed to do a timing analysis across multiple of these ECUs. So on the next slide, I want to focus a bit more on the actual software architecture and how to make a debugger aware of the underlying architecture. As mentioned earlier already by Olaf, is that the ECU runs on Hypervisor, the micrococos hypervisor from OpenSynergy. The hypervisor provides multiple virtual machines. In this example, we have 4 of those virtual machines, and each of those host an AUTOSAR OS. And to make such a complex system actually traceable, there's basically 2 main criteria that need to be fulfilled. One criteria is actually that the trace tool understands basically the underlying OS and hypervisor structure. This is what the debugger vendor typically calls OS hypervisor awareness. With an AUTOSAR Classic OS, this OS awareness is typically achieved by reading in a so-called ORT file. ORT is an abbreviation for OSEC runtime interface, meaning this is part of the OSEC standard and now also become part of the AUTOSAR standard. But this setup, this concept needs to be extended for our setup here, as I will explain. The issue that we're facing in this setup here is that we have actually multiple OSs separate by a hypervisor on virtual machines. And this concept of hypervisor virtual machines, multiple OSs, is completely not considered by this ORT standard. What we also have to keep in mind here is, okay, what's the actual intention of this exercise? As Olaf mentioned, we want to correlate simulation results from the INCHRON tool suite of a software timing model against the trace data obtained from the real hardware. And in order to do a really meaningful correlation of those both timing, simulation versus trace, it is important to compare a similar level of information, a similar level of details. And therefore, it's not sufficient to trace just the currently running task. That's what's typically done if you use the ORT file for profiling. In our case, we really want to trace the detailed task states of each OS task, meaning a task has been activated, not running yet, running, or waiting for an event, etc. Because this is actually the same level the simulation also works on. And for these special OS hypervisor awareness topics at iSYSTEM, we use our own proprietary XML format, which is shown here on this side. Such an XML file can, for example, be used to tell the profiler how the hypervisor, for example, signals virtual machine switches to a trace tool, or the XML can also be used to extend or first include an existing ORT file, as we see in this line, and then extend it with some additional functionality. For example, extend it with the possibility within our profiler to profile OS tasks. What this means, the XML file basically describes to our tool what kind of global variables need to be traced. Like in this case, this is the global variable that needs to be observed. And how to interpret the data that we get from the OS. Yeah, this basically takes me to the second criteria. The second criteria is that the OS or the hypervisor running on the target actually needs to reveal this data to a trace tool. Meaning, in terms of a hardware tracer, this means that the hypervisor and the OS need to write the relevant information that we're interested in into a dedicated global variable, basically to a memory access. And then the on-chip trace logic, like the Nexus trace module on the RJ50, captures this data when the CPU writes to it, and then streams it out to the trace through the trace port, and we record it in the end. However, I really want to emphasize that such a trace infrastructure may not always be in place when you start with your project, for example. So this needs to be created first, and this requires really a close cooperation between the trace tool vendor like iSYSTEM and the OS hypervisor supplier. In this case, it was OpenSynergy. And this project here was a very fruitful cooperation with iSYSTEM and OpenSynergy, which really led to very, very good results, I think. But really, my message to you is that you have to, in general, think about your requirements in terms of timing analysis really early on in your project, in an early project phase. And then you should discuss those sort of requirements with your hypervisor OS vendor and also with the trace tool vendor, just to make them, give them the time to prepare for it. Okay, on this slide, I just want to summarize again which objects we actually trace and profile in our tool. On one hand, we do, based on a full instruction trace, we profile the code and the functions of all the hypervisor and virtual machines. As you see here, each virtual machine has its own image or ELF file, and we profile those, all of them in parallel. Then we do a trace and profiling of the hypervisor and all the OSs running on the virtual machines. This is basically traced on based on data tracing, using the variables that are used by the virtual machines and hypervisor and the OS to signal the transitions. And finally, last but not least, we also, as I said, also trace the communication on the CAN bus. And as mentioned earlier, this is really essential and required for the later on synchronization between the traces of the various ECUs. Now this screen actually shows a real measurement on the target. Here on the top, you see how the hypervisor switches between all the various virtual machines. Actually, it's called virtual CPUs in OpenSynergy nomenclature. So we see this kind of a round-robin approach here. And further below, you see the tasks within the virtual machines, actually the tasks of the out operating systems running within the virtual machines. And here, for example, virtual machine 1, you see this task ECUM, for instance. You see the detailed task state here. Here the task is suspended for a while, gets activated, stays in ready state a little bit, then actually goes into running state and terminates and goes back to suspended state again. And within this task, you actually see down here on the CAN bus section of the profiler that the CAN frame gets transmitted. You see the timing of that frame from start of frame until end of frame. And at the end of the frame, you see that a certain signal mapped into a frame gets updated here. Obviously, those two recordings of the CAN bus and the software is synchronized to each other. And finally, all these trace recordings and profiles need to be transported somehow into the INCHRON tool suite to actually do the correlation against the simulation. The iSYSTEM trace analyzer exports these traces in a specific format, which always basically consists of a timestamp, give a timing information on different objects that can be exported, an action. An object, for example, can be tasks of an operating system, virtual machines, a CAN frame, etc. And the actions are certain events associated with the object, for example, entry-exit of a function or a state change of a task and so forth. And sometimes there's also a value attached to an object. For example, in this case, you have a signal within the CAN frame, which gets incremented, in this case, to the value of 43. And for the synchronization of the two traces, the concept is now to pick a unique synchronization point within the CAN trace recording. In this, for example, since the reason is obvious, because the CAN bus recording is the common time point for both of recordings. In this case, for example, we pick on both recordings here the CAN signal getting incremented to the value 43 on both of the exports. And now this is a synchronization point for both recordings. You see timestamp for the same event may be different on the recordings. This can, for example, be because of the trace has been started at different absolute times, but obviously they happen exactly at the same absolute time. And how the two traces now synchronized to each other and merged. This is actually done within the INCHRON tool suite. And I guess this is what Olaf is going to show you as next. Okay, and then I hand over to Olaf again.
Okay, thanks, Armin. I noticed that there's almost no questions so far. So I would like to again encourage everyone who's listening right now to also ask some questions for both iSYSTEM and INCHRON. Philip is available in the background to answer any questions, and we will also have some time at the end of this webinar to take further questions. So please go ahead, get your fingers warm and send some questions. So, okay, I would like to pick up this this part. So as soon as we have multiple traces available, and here you see again 3 traces. Armin has shown it in 2 traces, but it's the same mechanism. We would load these 3 traces with our trace merging tool and pick the event that is identical in all the traces, so that when you have the different traces that you have taken, they of course may have started at a different point in time, and then you would kind of set a trigger that connects these traces, and then they are basically running on the same time scale. And now we can visualize in a similar way as we have seen it before. These traces, you see this timing diagram uses a combination of the 3 units. It's the green one here, a blue one in the middle, and another green one on the top. And there's also the CAN bus included, and you see all synchronized timing behavior. So we have a direct correlation between the VM2 on this unit with data fusion in VM3 on this unit, and we can see exactly how they are timing correlated. In addition, you see here the data path, or we call it event chain. So this is the way data is passed from one task to another between this unit and tasks on this unit. And this event chain will eventually show that the data is going to this task here at the end. And there's 2 other event chains, and the green one, for example, is processed on the blue unit here, and then moved to the unit here up here, and you can see that both data paths will eventually join in this part. And here down here, the next event chain starts. So by this, you can easily visualize and analyze what's going on in your overall system, even if it's spread across multiple boards, multiple CPUs, and you can see, analyze, visualize the overall timing behavior even across units. And here again, you can also see timing requirements that have been that are evaluated automatically. You see this little green bar and the timing of an event chain here, 28 milliseconds. So at each point in the development, you are able to immediately see where the requirements that have been set on the system or architecture level where they are met. So they're the same requirements that we used on the simulation, and the simulation of these timing behaviors of the 3 units and the event chains. The same requirements can also apply it here with data that is based on a measurement, for example, by the iSYSTEM blue boxes. So another aspect I would like to take your attention to is fault injection. So in a safety critical system, it is very important that even if you have a fault in some parts of the system, that the rest of the system is still running smoothly. And one aspect to do this, one method to do this is using a hypervisor. So in this example below here, you can see that for some reason this VM2 is crazy overloaded. So there's a fault in this section. So you can see from the requirements that the events here in VM2 violate the timing requirements, and you see also RTOS failures, which means that here some tasks are activated too often and cannot be handled. And you can also see from the diagram that there's a huge overload in VM2. But you can also see at the same time that the hypervisor still lets all the other VMs run smoothly. So it separates the execution of tasks in VM2 from the execution of tasks in VM3, and the VM3 related requirements are still fulfilled, although we have an overload situation here. This is also important when you're designing a system, that you check if the system still works okay, even if some parts have an overload situation. Yeah, so that was basically the information we wanted to provide to you today. As a summary, you can say it's looking at timing and performance. The idea is to work on the simulation and worst case analysis, taking your system requirements through your architecture and system and software architecture, and do this in a incremental and improving way. So you take it step by step, improve it in every step, and then check with every step if your requirements are still fulfilled. You can do this before you even do your implementation, just by using a simulation. So you will be able to find and fix many timing errors, many errors that are related to timing and performance very early in your project, by just looking at the simulation and optimizing your architecture and checking your requirements. Then, of course, as a next step, you will implement the system and analyze the system using the tracing capabilities of iSYSTEM, and that will give you a second circle, so you can update and verify your system using the same requirements you had on the simulation part. You can also use these requirements when you check your implementation, and then you can update and optimize your implementation, or may have to go back to see if the requirements can be fulfilled. So this is also, you would do this in a circle and work between implementation and architecture until you have all your requirements fulfilled the right way. And then, and this is kind of an outlook and something that's not covered in this presentation today. You can also take this further and create a virtual target from the measurements that you have done. So you can kind of simulate based on the your measurements, and by using simulation, by changing some of the values in the simulation, by bringing some statistics in there, you can actually increase your test coverage that you will not be able to do with just having an implementation. So timing and performance optimization is a process that is through all of your project, and it always goes in circles. You should start it as early as possible in the system, in the architecture and requirements phase, and you should still keep it in the loop when you look at your implementation and trace it. And if you want, you can also take it further to virtual targets. Yeah, so that's all from me today. Thanks for listening. Thanks for your attention. We will be here another 15 minutes to take all your questions and have a discussion. If you are interested, this webinar today was recorded, and a recording will be available early next week. So if you are interested in a recording, then just let us know, and we will provide the link next week. Yeah, so I'm happy to take all your questions, and thanks again from SAPMed, iSYSTEM, and INCHRON for your participation today and for your attention. Thank you so much, and see you.